Hello, welcome back to my YouTube channel. I am Thalitakum Hutajulu from Udayana University Mechanical Engineering student. Okay, the purpose of this video was meant to fulfill about linear algebra and also to educate about linear algebra. Okay, my reference is from the book Linear Algebra. Kuldeep Singh Linear Algebra Step by Step. Okay, in this section we will learn chapter 4 about inner product space. So this is a contents. 4.1 Introduction to inner product space, and until the 4.4 orthogonal matrix. 4.1 Introduction to inner product space. So a definition of inner product. An inner product on a real vector space V is an operation which access to each pair of vector u and v, a unique real number u and v. So this is x1 which satisfy the following x1 for all vectors u, v, and y in V and all scalar k. So commutative law, 1 commutative law, 2 distributive law, 3 taking out the scalar k, and means the inner product between the same vector is 0 or positive. Example of inner product. So we have let's see 0 and 1. So their inner product. So inner product from F and G. So we have a formula. And now we substitute C, Fx and Gx to the formula, and we will get a result. This is a result from the solution from the F and G. Okay, properties of inner product. Let U, V, and W be vectors in a real inner product space V, and K be any real scalar. So the properties of inner product: U, this is the properties of inner product. So this is a proof from the properties number 1, proof from properties number 2, and proof from properties number 3. The norm of leg of a vector. So the norm is defined in the same manner for the general vector space V. So room O equal, this is a positive root. So example, we have A and B. So root A and B. So we get notice the entries in matrix B are 10 times the entries in matrix A. The norm of matrix B is also 10 times the norm of matrix A. Okay, we have example. So from the example we have to now see is 0 and 1, and we have the formula. So for the first situation or problem, we substitute the f and g to the formula, and we get the and station 2 we have the formula, the same formula. So we substitute C to the formula, and we get the hence. Get this. For number 3 too, we substitute C to formula, the same formula, right? And we get the this is. For number 4 too, we substitute C to the formula, and the hence from that we get this. We will get the result. So this is a vector G, F, min G, and F, min G. So from the some norm are not defined in terms of the inner product. So then the following are important norms in this space. This is a 1 norm and 2 norm and infinity norm. For example, from this following are important norm. Example for it, we have a vector min 1, 4, min 9, 7, and transpose. So the 1 norm is a 1 norm, and this is a 2 norm and the infinity norm. Properties of the norm of a vector. So this is a properties from the norms. This is a proof bukti dari from the properties of norm number 1, properties proof from properties of norm number 2, and this is a proof from properties number 3. (4.2) Inequalities and orthogonality. For general vectors such as polynomials, metric, and function, a simple basic is one where the set of vectors are equally orthogonal or perpendicular and have unit legs. Example U and V be in R2 or R quadrant or root 2. So for number 1, we U and V equal U times V. So U and V, U times V. So the hence from the formula we get the (11). For number 2, So the symbol, it means the leg of vector. So leg O, we have a basis, and leg V we have this. So leg U times leg V is this is. For the leg U plus leg V, we get this. This is a result. And from the leg U plus V, so we get this. So this is a application in coordinate cartesians. So this is a leg U, leg V, and leg U plus V. Inequalities. Two inequalities. So this is inequalities, yeah. Cauchy-Schwarz inequalities and Minkowski inequalities. See word. Let V be an inner product space for all vector U and V. So this is A, B, and C. This is a leg U, leg V, and leg U plus V. Remember, this is the donkey theorem. If a donkey is at station A and the foal of this located at station C, then the donkey will travel the shortest distance along AC, not BC, and then AB, and then BC. The inequality leg U and leg U. So this is a part from the example. Then I'll learn the reverse part. So we get this. This is a orthogonal vector. Two vector U and V in Rn are said to be orthogonal or perpendicular. U times V equals 0, and then U, and we get the U and V equals 0. So two vector U and V in the vector space V are said to be orthogonal. This is if the vector U and V are orthogonal, U is orthogonal to V, or vice versa. That is, V is orthogonal to U because U V equals 0. VU equals 0. Consider the vector U and UV, W, and X in R quadrant. Positive is negative. UV is 0. This is application in coordinate, right? So U and V and W, U and W is negative, and U and X is positive. So U and V is 0. For example, we have V and K. So multiplying coefficient P and K. So solution, from that we get the we make to the, so we times the all from p and k to 1 to number 1 and min 1 to number 1, right? Number 1, so we get the 0. So we conclude that the given vector p and k are orthogonal because p and k equals 0. This is an application in coordinate Cartesius. Example, we have matrix 2 times 2, 22. So matrix A and B. Remember that ranks of a matrix is the addition of leading diagonal entries. So transposing and multiplying, we get this 2 and min 2, so 0 only in the part. So matrix A and B are orthogonal because AB is equal 0. Let the vector u and v be orthogonal in an inner product space. Then formula. So every vector in an inner product space V is orthogonal to the 0 vector u vector Prof from this. Okay. Since P was arbitrary, every vector V is orthogonal to the 0 vector. This is a normalizing vector. A unit vector U is a vector of leg 1 or a norm of 1 that is U equal 1. The process of converting a given vector into a unit vector is called normalizing. So every non-zero vector W in an inner product space V can be normalized by setting the formula. Example, this is a vector P. So we from the problem we have to know P is, this is a P. So this is a formula. The normal this vector P is given by the formula. So what the leg P? So leg P quadrat. This is. So this is a formula. So we substitute to the formula and we get this. So multiplying the coefficient in here, and we get the hence from the normal this unit vector. This is a hence or result. For example, A1 and A2. So A1 times A2, we get the 0. So this is a orthogonal. A1 and A2 is a orthogonal perpendicular. So, and also A1 like A1 and like A2 equal 1. So this is a normalist vector. This is a application in the picture or in the coordinate. This is A1 and A2, and this is in the let V be a finite dimension vector space with an inner product, a set of vector V, where V is called an orthogonal set if they are memenuhi persyaratan ini. Okay, example, B is A1, A2, and A3. So from this we have to know A1, A2, and A3 with transpose. These are only A1 and A2 transpose, and with times A1 times A2, so we get the 0. So this is orthogonal. And leg A1 equal leg to A2 and leg A3 equal 0. So this is verify that the leg of vector. This is orthonormal too, and the normalish. This is B is not only an orthonormal set R3, but actually form an orthonormal basis for R3. Orthonormal basis. Reduction to an orthonormal. So this is a basis from the orthonormal, so orthogonal and normalist. Example of orthonormal perpendicular unit basis. This application noted that our usual x, y, and z are orthogonal to each other. So perpendicular unit, orthonormal, this is for R3 and R2. Properties of an orthonormal basis. So this is a formula. We have already learned about the formula in the previous chapter. So from the picture, we have to know this vectors are linearly dependent but not orthogonal or not perpendicular. So orthogonality, independent but independence, not orthogonalist. Example, U and V are orthogonal in R quadrant. U times V, and this is orthogonal, right? Like Q quadrant is 2, so this is a normalis. The normalis. An orthonormal perpendicular basis axis for R quadrant. So this is application in the dimensi 2 dimensi. This orthonormal. Generating orthogonal vector. So this is a projection U of U into U. So from orthogonality signifies a certain kind of independence or complete absence of interference. Noted that the projection of orthogonal vector is 0. Example, so this is a formula from the orthogonal vector. The formula, we have to know V1 and V2 is 3, 0 and 1, 2. This is a formula. So we substitute C to the formula and we get the result. So this is a result. This is a application in the coordinate Cartesius. So this is a orthogonal vector, right? The orthogonal vector that we start with one of the given vector V1, so then we create a vector orthogonal perpendicular to it by using the other given vector V2, and we get the V1, V2 and P1 3, 0 and V2 is 0, 2. So this is a procedure, step by step. The steps are known as a Gram-Schmidt process. This is a Gram-Schmidt process. The Gram-Schmidt process. So the vector P are orthogonal to polar basis. So the formula. Example, V1 and V2. So V1 equal V2, V1 equal 2 and 1. So the formula, we substitute C to the formula and we get the basis. So let P1 quadrat equal to we make like Pythagoras, we make Pythagoras formula, and then we substitute C V2 P1 we substitute C to the formula. So from the formula we get the P1 and P2. So we make the leg P2 is the, so from the law of incest we get this. So we get the U U1 and U2. This is a plotting. There's orthonormal perpendicular unit basis. This is our given basis, and this is an orthonormal basis. Orthogonal matrix. Orthogonal matrix is orthogonal matrix unimportant in subjects such as numerical analysis because this matrix have good numerical stability. Example: let key U1, U2, and U3, where the U1 is set. So we transpose and we times 2 this and we get this, and we multiply numerator the denominator by this and by this, and we get this, taking out a scalar multiplicity. Okay, this is a proof from this. So key is an orthogonal matrix. From the proof, we have to know the key is an orthogonal matrix. Properties of orthogonal matrix. Example. So we get the key U and Y. So from number 1, we get this 5, number 2 5, and note the key U and key times W equal U times W. This is a profession. So from profession, we have to know the key is an orthogonal matrix. Key times U and key times W equal U times Y, W. So this is a proof. From the proof, we get this. For example, we have key and U. So leg O is this, and now for number 2, key times leg key times O quadrat is 5. So this is a application for an orthogonal matrix key and the leg of vector key U and U are equal. Applying an orthogonal matrix key to a vector U may change the direction but not the leg. An orthogonal matrix key in key U will just rotate the vector U. So an orthogonal matrix preserve the leg of a vector, and if a transformation matrix prefers leg, then it is an orthogonal matrix. Okay, triangular matrix. A triangular matrix is an n by n matrix where all entries to one side of the diagonal of 0 are 0. A is an example of an upper triangular matrix, and B is an Example of a lower triangular matrix. Another type of matrix is a diagonal matrix. A diagonal matrix is an n by n matrix where all entries to both sides of a leading diagonal are 0. So identity of matrix 1. Another example. A diagonal matrix is both an upper and lower triangular matrix. Key are factorization. So let P an n by n matrix with linearly dependent columns. We can factorize matrix A into R key R. So where K is an orthogonal matrix and R is an upper triangular matrix, so Rx equals C in matrix form this. And we get the C until Cn. For example, we have a matrix A. So matrix A we times multiplying to the Q1, Q2, and Q3, where the Q1 where the Q1 to this is a Q1. So the matrix key transpose. So transpose from the matrix key. With times to this. And we get this. So how do we get this orthonormal vector from the matrix A? So this is a formula. From the formula we get the orthonormal from matrix A. This is a Gram-Schmidt process, right? So we get the substitute to the matrix A, and we will get the result. Summary. Orthogonal matrices are square matrices whose columns are orthonormal perpendicular unit vector. We can factorize an M by N matrix whose column vectors are independent into A equal RK. Okay, this is my video. If I mistake, I say sorry, and finally, thank you for watching.